All right, class. I thought I'd try to break down the idea of rate laws and their relation to concentration about as simple of a way as I can. So imagine that we have reactants A and B in a box that will produce C. Okay, and so probably in keeping with color coding here, let me go ahead and switch this out. So will make A red and B will be black. Okay. So so what I did was is I've come up with three hypothetical boxes here that all have the same fixed volume, so thus we can view things in terms of molarity, which is moles to volume. And remember, moles are nothing but collections of molecules. So what's true for number of molecules is obviously true for number of moles. Let's not forget that. So this say that this reaction, which is A plus B equals C, has been determined experimentally to have a rate order of K times A times B squared. So obviously it's second order with respect to B, first order with respect to A. So if we wanted to know which of these would have the slowest rate of reaction happening, and then the next slowest, and then the least slowest, we could just simply plug this in with our known molecular amounts, and we can determine this. So let's take a look at box one. We see 1, 2, 3, 4, 5 molecules of A, and we see 1, 2, 3, 4, 5 molecules of B. So we take our constant times 5, which is for A, and then 5 squared, which is B, and so we would have a rate at 125K. Box 2, we have decreased the amount of B significantly to only 3 molecules as opposed and increased that of A, represented in red. So we would have K times 7 times 3 squared being 9, and we would have 63K as our rate. Over on box 3, we reverse the situation. We raise the number of molecules of B, represented as black, to 7, and decreased A to 3, and K times 3 times 7 squared is 147K, and this is hardly surprising because our rate equation here shows that B has by far the strongest effect on the rate of reaction, more so than A. And thus we can rank box 2 to box 1 to box 3 in order of increasing speed of reaction, or we could view it in terms of less slowness. Either way is the same thing. So that's basically how you could view this down to a molecular level. Now, of course, this only applies because they are all in the same fixed volume. If one had a significantly larger volume than the other, that would greatly affect the reaction rate because it would affect the opportunities for collisions between molecules, which would make the actual reactions happen. More space, we presume we would have less frequent collisions between molecules. So this only works when there's an implied similarity in overall volume that has to remain constant. We also would assume that temperature and pressure would be constant in these as well. As just to always keep in mind that those are factors that if manipulated will change the overall reaction rate.